Good evening and welcome everybody. This is Obi-Wan Pez for Simplex Pachinko. We are gonna start class for differential equations. We are going to be working on section 2, which is all about separability of differential equations. And we're going to, so as I figure out what screen I'm on, we're going to head back to the event stage here and unmute myself. Joining us tonight we have Zach, Eat of the Two-Eye Pie, and Femvox Fan. Awesome, thank you. I knew that one of the various methods of fixing that would work, so... Alrighty, so... Yeah, I had set up a couple of the security measures in the background, but unfortunately, that means like if you don't have whatever verified stuff, that then Twitch will yell and then won't let you do stuff, and that's not very nice of them. Okay. So to start with, for tonight, I'm gonna welcome to the stage Eat of the Two-Eye Pie. That's Zach. Whenever you're ready, sir.
Hey there. Yeah,
Hey.
no, I'm ready.
Awesome. And in terms of audio levels, how's everybody else doing? Yoma, good evening.
I don't know how I sound, right?
Yeah, that's what I
It's
meant.
hard to tell.
Danny, oh well. Yep. Well, thank you for lurking on in. And feel free to join any other time. We got our Mondays, or on the off Wednesday, you just happen to be able to do something, that'd be awesome too. You know, no worries. As they tend to say over here. Yep. Sounds great. Phobos, good evening. And if anybody else was planning on joining in, feel free to join the Discord at Penn Centers. And of course, I don't have that screen up. Yins. You can join Penn Center's Discord. And then I would, if you're going to join just ahead of time, let me know. If you are somebody that is known to us, then we're going to let you in, so it wouldn't be a problem. But I hope you're all having a wonderful Wednesday. We just got here, what, 3 months ago now, and the kids are wrapping up school, and daughter had her leavers service because she is leaving that school. Granted, it's only been 3 months for her, but some of the kids have been there since they were like 6. So it was an interesting time. Alrighty. So, I guess, Zach, do you want to start us off and recap just real quick what we did?
Let's see here. So we had a lot of conversations about order and the classification of differential equations into ordinary and partial. We talked about the order of a differential equation. We talked about the, let's see here, linearity of a differential equation. And I seem to always forget the fourth one, the fourth axis we're supposed to put these on, like formally what we call it. It'll probably come to me once I have it in front of me. But we basically classify differential equations into categories based on their attributes.
Yep.
And then we also talked about sort of the history and different kinds of problems that were solved, and practiced even classifying a few. I missed the last half, but if I understood correctly what you were talking about what it means to be a solution to a differential equation, and testing, like taking derivatives and actually verifying that the derivatives do in fact satisfy the equation.
Yep.
I think that's like the big idea, is the overview.
Okay. So if we go with this one here, what would the classification for this particular one be?
Oh, it's a homogeneous and a homogeneous. I remember now.
There you go.
I remember the fourth one. I thought of it. It came to me because you made one inhomogeneous, and I instantly thought of it. So let's take a look. We've got ourselves that is definitely nonlinear. So the thing that sort of sets me off as saying this is nonlinear is the fact that we have a y-squared term. Right? So definitely nonlinear. We have something that is of third order, because I'm looking at the third order differential equation. Like it has a third derivative in it, and as the highest order derivative. This one's tough to be able to show, but this one is ordinary, and I only know that because we are using the prime notation. So that tells me that these are functions of a single variable, and that's what makes something ordinary. I will say, personally, I prefer using the dy dt method, just to be clear, and using non-partial things just to emphasize the fact that this is an ordinary. But in order to be partial, you'd have to have multiple variables. And then what do we got here? We got our ordinary, and this is inhomogeneous, because you can't separate this into sort of an x and y part. I know I'm not supposed to use separability, but like that's the non-technical way of saying it. Another non-technical way to say it is to say the right-hand side is not zero, but like I can't clearly separate this into a function of x and y, or sometimes it's going to be with t and y or something like that. Yeah, that's sort of the key. The equals 0 thing is tricky because you could subtract the 10x or 12x to the fifth to the left-hand side, and this thing would still be inhomogeneous. So we have to be very careful.
That's a favorite thing of mine to do.
I was going to say, I was almost expecting you to do it, because I'm like, well, what are you going to do? That's good, though.
Yeah, so...
Yeah, the function of the independent variable is the big idea there.
Like the most technical way to talk about it that I know anyway. There exists a function of the independent variable alone that is distinct from 0. So in this particular case, even if it was just equals to 2, right, that's still a function of the independent variable by itself.
Yep.
Even if it's just a constant. And distinct from 0, it's just not 0 itself. So
this plays a role later, I will add, for those that haven't seen this before. That's a very important role that will play. And solving for 0 versus solving not for 0 is actually useful in a surprising way that I won't spoil. But
you could say which section, that's fine.
Well, it's fine, but like I remember when I actually got to teach this class once, only once. But when I did, I remember going through and preparing the lesson for that day, where we talk about what it means to solve inhomogeneous nth order ordinary differential equations. Surprise! It's like, oh, that's true. You do get a 0 there, and the proof as to why the method we use works is sort of important. That we have the 0 part and the non-zero part. Spoil us, Foho says. I don't want to. You want spoilers? This is a rare opportunity to give spoilers, right?
Yeah. So I would say, especially during nth order, and usually the ones that we're going to be looking at anyway are going to be linear.
Yeah.
So just go like that. move that over and right. Right. So at least the nth order linear differential equations are the ones that we're going to be looking at. And I guess we can also say ordinary, but So yeah, these are the ones that we care about for the most part. There are many other... A bus with a spoiler. Interesting. Yeah. Distraction.
Yeah.
So yeah, we're going to be checking those out. There are many, many other types. And if anybody is taking a master's level differential equations class, there are 2 of them up there that I took that are really fun. One is partial differential equations, which spends about a month out of a 3-month semester looking at all of the ways that you can do analytical solutions. And then you spend the other 2 months going, well, analytical solutions don't really work anymore. So now let's move on to numerical solutions.
This reminds me of a comment I made. I was actually taking an advanced ODEs class, sort of a mix between ODE, PDE, introduction to PDE type thing. And I remember in that class, my son had his teacher came up to us and he said that his teacher said, we can't, you shouldn't guess in math class. Like we're not supposed to do this. And then that day, I'd had my professor say to me, all we can do is guess sometimes.
Yep.
And I was just like, the contrasting on the same day, and I'm like, how funny is that?
Now, to be fair, you can always guess. It's just that you have to have an actual, reason to back that up afterward. In the case of differential equations, it's like, well, we don't really have any other way to do it, so that's the best we got. And for elementary ed, I can definitely understand the sentiment, but at the same time, I'm not sure we should be just telling the kids absolutely do not guess.
That's right.
That's a great thing to develop your intuitive sense of things, but not something that you want to be like, this is the only way I know how to do things.
Right.
Okay. So yeah, classification looked at in that's fine. Going through again, typically this is the order in which we state things. It's not like it's absolutely hard and hard set rule that you have to do them in this order. It's just kind of like that, new red plastic, that particular order that we just intuitively know how to put things, how to put adjectives in a specific order, and it sounds wrong if you do it any other way. Here, again, same deal. Once you've had a lot of experience with differential equations, they just go in this order. So this particular one here, again, ordinary, because we don't see a partial derivative anywhere, and you really have to use that nice notation. I do also prefer typically writing it out in Leibniz notation, which uses in this case, right, that one would be third derivative of y with respect to x 3 times. And again, this is really helpful because if it is a partial derivative, it would look like, third derivative of y with respect to maybe x twice and z once. Originally, actually, the D notation that was used here was also script, so it looked like this. So if you look at Leibniz's original notes, almost all the ordinary differentials are also like this. The only difference is that you're just always going to see x's on the bottom, and there is only one independent variable, so it didn't actually matter. But for our purposes, we're going to say that it does matter just because we're going to focus on the fact that this whole thing only has one independent and one dependent variable for an ordinary differential equation. which may also be one of the reasons that I get tripped up in tensor calc, but that's another story. All right. Anything else to add, Zach?
Not right now.
Okay, cool. So we move on. And from last class, is this the one? Yes. Okay. So how might we be able to tell whether a given differential equation even has a solution?
Well, I mean, there's that guessing method again. Right? I mean, you think about it, like I think last time we established that like there's the equation y prime equals y, right?
Yep.
And so, like, really what that equation's saying is there a function that has its own derivative? And the answer is yes, right? I can think of a function that does that. That's e. Or I can think there are functions that are like, well, what about what's another good example? What about y double prime equals minus y? I can think of a function that does that. That's the sine function, right? That would be a potential solution of that. So those seem to have a way of being able to solve. Those seem like solvable. So I'm trying to let's think about which ones wouldn't have a solution. Why would something not have a solution? Maybe if and I'm trying to sort of build up the idea. I know the idea too, I think, but I don't want to. I want to see if we can build it. So, how about something like? What's a good example of this? We could do.
Femvox, I absolutely agree. How many famous mathematicians just had lucky guesses over the centuries that ended up being correct? Yes. I'm not giving you a number, I'm just saying yes.
Let's see here. So, I mean, how do you want to talk about this, Obi? I don't want to go too fast or too slow or anything, but I mean, I know ultimately we're getting to like the Picard theorem here, but I want to like sort of build that up for viewers, and I don't know that I've actually had to say this out loud very often. So, how do you want to talk about it?
Okay, so like, where might we have a differential equation that has just absolutely no solution to it? So, the most obvious thing to pick would be what?
The most obvious?
Yep.
So I mean, it's not. Just a second. I was looking at something. The obvious ones. Well, you could pick like a PDE that we don't know the answer, like the Black-Scholes, or we could pick like the Navier-Stokes if you want to go really crazy. But
So
those don't have
if I want to be a complete pain, that will have a solution, right?
If,
we just don't know what it is.
Like, we don't know what it is, but like it'll have something. But if you want to do like how about
from an analyst perspective?
You want to do something that's not. Oh, I see what you're getting at. Okay, so you want to do something that wouldn't have like an antiderivative or something like that. The derivatives aren't going to exist or something like that. That would be reasonable. I like the idea of where that's going. You need to have derivatives.
Right, so in order for us to say,
fair.
like, there's no solution to this, definitely, right? If the derivative doesn't exist somewhere, then yeah, okay. The original function is not going to have a differential equation that corresponds with it for that particular location.
Right, so like the function absolute value x won't have a derivative at 0.
Yep.
So that kind of thing. If our solution involved the absolute value of x somehow, or like our different, or we had some. I'm not saying it right, but
Well, I mean, what's the one-word solution here, I guess? Right, so the derivative is
does not exist, right?
Yeah.
It's not C1, you might say, or at that
probably
point.
undefined.
Mm-hmm.
Either way you want to go with it.
Yeah. Yep.
Okay. So by contrast, if we want to say that, yeah, there is at least a solution,
If there is at least a solution, so you want me to talk now?
Sure. Go for it.
Go for it. Okay. Well, so there's other things that could happen too, right? You could have something like y prime equals x, which I suppose technically could have a solution, right? There's this other component we need to think about. Just as another example, you could have y prime equals x, and that would give you y equals 1/2 x squared plus c. So there's a sense in which we could, you could have a function of the independent variable as well thrown in here, which is going to play into our definition.
Maybe.
Of like what it means for a solution to exist eventually. Again, I'm trying to anticipate a little bit.
That's okay. And I'm trying to reread my notes to make sure that I've covered all my bases. So. So in terms of like having a differential equation like y prime equals y, like y prime equals x, like y double prime equals negative y, or any of those other ones, then we want to say there's going to be at least, a solution will exist provided that our y prime, and we're just going to go with y prime, so like in terms of the y double prime up here, this would be like, y prime prime. We're only going to decrease the layers, if you will, one at a time. So we only decrease the order one at a time when we're looking at fairly simple equations like this. So if we have a function that is y prime equaling some function of x and y, it doesn't even matter. It can be literally any function of x and y. We will at least be able to say that a solution exists provided that what is true about f.
F has to be continuous.
Okay.
Right, so we can say that, right? Now, there's another condition that's a little tricky. And that's why I didn't want to, but it's continuous, and specifically continuous in our x variable. It feels like a silly thing to say, but that's important to say.
So if you're talking about an ordinary derivative, this one is
it's like
ordinary.
I don't want to introduce the word Lipschitz without your permission. So like I
actually don't know that one offhand. So
okay, because like Lipschitz involves having constant slope. You always have you can control the slope of your function. Basically, is what that means.
Okay.
But there's a theorem that basically says you have to be continuous in t or x, right? Usually I think in t, but x, and Lipschitz in y. Is how I've heard it said. But I don't. If you're just saying continuous in y, that's fine.
So the way that I've always had it was it's just continuous on an open rectangle.
Sure, continuous. That's necessary as well.
Okay.
Again, I'm sort of going to let you sort of take the wheel here so that you can control the conversation. If I will go off the rails if you let me.
I guess if there is an important nuance or distinction, then I think I would want to hear about it, because I probably don't know beyond much
Okay.
beyond this.
Because like the one thing, so when I've heard it said, and like so this is from different dynamical systems when I took that class, and I'm reviewing the definition here just as a reminder because I don't use this concept all that often. It's used often. The concept here is that you can take the distance in your you have what's called a Lipschitz continuity in y, but your continuity in x, which basically says that the slope at which your of your function at any point is controlled under some k value. You can always find a k such that the distance of f of x. So basically, in analysis terms, the magnitude of f of x1, 2 is less than k times, or less than or equal to k times the distance x1, x2. But that's basically a slope condition.
You said the magnitude of the distance between x1 and x2? It was kind of cutting in and out there, so...
Sorry about that.
That's all right.
And I'm also going to say, corrupt converter, my answer is C, none of the above. I reject your notation.
Is that on Discord?
No, look at the chat. There's a... Sorry, I had to... saw that.
I don't actually see any... Oh, there we go.
I mean, I would honestly, just the way I'm looking at it, the answer would be B, from my perspective, but...
I see. Yeah, all I saw was I'm running a poll to prove a point, and I was like, where's the poll? But...
I would say B, corrupt converter, but I would say... Anyway, yeah,
I would also say B, but at the same time, I would say that it needs to be clearer. This is the same as those ridiculous online things where it's like, oh my goodness, the best bots ever.
That get deleted.
Ban.
Schrodinger's logarithm, exactly right. That's right, Fembox.
Yeah, that's the same thing as what I see when we get those ridiculous online things where everybody's arguing about, oh no, do we multiply or do we divide first? Yeah, it's even got bot in its name. That's just a little too on the nose, man.
I just turned on the and it's got I knew I had three.
Knew you had what?
It's just like I knew it had 3 T's. There's a Brian Regan sketch where he spells cat with 2 T's. Yep. I knew it had 2 T's.
I love Brian Regan. He's the best, cleanest comedian that I know.
Yeah, he's good. Anyway, we'll talk about Lipschitz, not Laplace transforms. Lipschitz continuity, though.
We'll also talk about
again,
Laplace transforms.
Yeah, we'll talk about Laplace transforms later. But Lipschitz continuity has to do with, and there's a nice picture here if you want to see. I'll put it in chat.
Yes, please.
We just ban them, Femvox. That's what I do. I just ban them. They get banned for life.
Yep.
Sorry,
and then I also report when I get time, which also kills the possibility of them reusing the same phone number.
Oh, that's nice.
They'll eventually get IP banned, but most of them are using a spoofer anyway. But the dumb ones don't.
The dumb ones.
Which, yes, for some people that would be all of them. But...
Yeah, basically.
Okay, so if we have this open rectangle which is containing that particular point, x0, y0, that technically should be in here somewhere. Yes.
But again, I want to make sure I'm using a consistent definition for you. How are you going to talk about this? Because it may be equivalent.
Okay, so comma, right? Because the way I started this sentence is slightly different than the way I actually started it before. Oh well.
Sure.
Solution's going to exist if our y prime is equal to whatever function on x and y is a continuous function on this open rectangle, as long as it's defined on the real... You know what? That's not real numbers. That's just our rectangle.
So, and Phobos's question is really interesting too. Why a rectangle? Like, why would we want to choose a rectangle? Why not like ball or something like that? Or any other shape?
It's just basically saying, like, we're going to have our boundaries, A, B, C, D, like this. And then all that we're doing is we're going to say that the solution will exist on at least one open subinterval. And it's going to be like A1, B1 as a subset of, subinterval of A to B, such that x0 is on A1, B1. So the rectangle convention is really just setting like ultimate boundaries. It's really kind of the easiest way to do it. If you want to have an alternate geometry, you could probably do that. But it's not going to be like so much of the stuff was in real analysis, where it's just like we're always going to create either a circle or a sphere around this particular point. This one's just saying, okay, set your boundaries A to B in the x direction, C to D in the y direction, and then we'll deal with minutia later.
And you can always fit a ball inside of a box anyway.
Right.
Right. Like, so in the end, you're almost splitting hairs, but the convenient way to define this is in terms of some epsilon distance. Like, usually you like to define integrals, for example, in angles. And so that's like the most convenient shape for an integral. Though you can use balls. It's just that they have different geometry.
Yeah, and in differential equations, it's going to be a lot harder to consider a round shape because of the integrals, like you said.
I see what you did there, Phobos. So you can probably fit a ball in a box. I see what you did there.
Okay. It opened the door to Femvox, and the bots roll in. Yeah. I mean, now that you have done your first time chat, I can turn that back on. It was all first time chatters must have a verified either email or phone number. Which, oh man. Okay. But I mean, it's a good point. Like, not everybody has both of those things, and I'm not sure if it's one or the other or both, or could be a pain. Anyway. So I guess another interesting point to this is that when we start talking about like the notion of separability, we're going to be taking two integrals at once. And one of them is in the x direction, and one of them is in the y direction. And so if they are, generally speaking, they're going to be not indeterminate. That's the other word. Oh man, indefinite. There we go. Most of the time, in general, they're just going to be indefinite integrals. There is the possibility that we could be taking definite integrals in both directions. So I think that's another reason for the rectangle, is that we're just saying, okay, it's A to B this way, and it's C to D this way, and that ensures that we have...
The point here is that your function's continuous, like you're saying. What I was giving you is actually a weaker or a stronger condition. Or, I guess it's a weaker condition because I'm not assuming as much. So what you're doing is absolutely fine. It's just that you can actually do better, and I guess I've learned the do better version. That's why I was hesitant to go there unless you wanted to. I know that some mathematicians like to give you the strongest result possible, or the weakest result possible, or whatever. What are the minimal set of things that you have to require in order to guarantee a solution? So the minimum is technically Lipschitz continuity, which is a notion than continuity. But I'll leave it there for those who are interested. Go check out the Picard-Lindelof theorem. There you go.
So in this particular case, we can have what's called an existence proof, and we could say, if we wanted to, let's do, yeah, we'll do an easier one. This is also going to slightly cheat and use the sorry. Now, you know what? Let's do an easier. Oops. Let's do a slightly easier one. Easier one. Alright, so y prime is equal to the secant squared of x. So in this particular case, we want to show, like, where is, where, over what interval or intervals on, let's go easy here and just say that x is going to be from negative 2 pi to 2 pi, and right, our domain is just going to be, you may have something to say about that, Zach, sorry.
Oh, you're fine.
Okay.
Continue. I mean, so, I see what you're saying, that I'd keep it open just to be safe.
Okay.
But, well, hold on, you're doing you're secant x? Yeah, you'd have discontinuity. Is that your point? There's going to be discontinuities here.
Right, so if somebody was just like,
okay.
This is the overall domain that we're going to be using for this particular problem, or all problems of this particular type.
I see what you're saying. Sure.
Then probably they would state either it's going to stay open or it's going to stay closed, but I don't care. This is my, like, overall domain, and then you need to show over what subdomain these are going to be. Oh, you know what? That's a good point. I did say right up there that we're talking about an open rectangle.
Yeah, I was going to say I would keep them open. But even so, you're going to have issues with continuity.
Yeah.
Especially with the antiderivative.
Over what interval on this? Do solutions exist? Then also, which contains the point pi over 4 comma 8?
I have to think about that for a second. You would take... Well, you would have to make sure, first of all, that the y-primed function... Let's see. We need to be continuous in t, so that means that secant squared x is not have to mentally do this. This is a little harder. So we're going to be on negative pi over 2 to pi over 2, if I'm not mistaken, on the that's going to be the domain of interest, I think. Because you can make a function from negative 2 pi to 2 pi, but the domain that we care about contains the point pi over 4, 8. So specifically that input value needs to be in our domain of interest.
Yep.
And without a picture, I had to make sure I can picture secant in my head. That's a hard thing to do, by the way. Like basically, what I'm doing is I'm taking the cosine squared of x, and I'm taking the reciprocal, right?
Yep.
Except I was taking the reciprocal of cosine x, so I might have messed that up.
You're talking to a trig teacher, so I mean I've been living.
Yeah. Somebody who like, I don't use secant squared of x all that often, but I'm basically taking cosine squared of x and taking the reciprocal function of that.
Right.
So it's not a big deal.
But in terms of at least the x values, the angles, right? You should be able to fairly quickly determine which ones are just impossible.
Yeah, right. That's basically what I was doing. The zeros is what I'm interested in.
Yep. And you don't even have to pay attention to the fact that it's squared.
Yep, exactly. That's what I mean. Is the negative pi to pi is what I'm. Sorry, pi over 2 and pi over 2. That's what I meant.
Okay, so that one is going to be your domain of interest down here. Yeah. And then, again, generally, up top here, over what subinterval or subintervals will any solutions exist?
Right, so basically, take your interval from negative 2 pi to 2 pi. You're going to take that and split it into sections based off of where the zeros are, right? The points of discontinuity, where there's a zero, or I guess an infinity, since you have asymptotes, where cosine squared would be 0, cosine squared x. Those are going to be at, well, not exactly multiples of pi over 2, but pi over 2 shifted by pi continuously down the number line, both in the positive and negative directions.
And just real quick, yep, Stooky, no problem. Don't worry about it. We hope you have a good rest of your what is it now? Afternoon? Yeah. Afternoon, evening, what have you. And, yep, thanks for the lurk. We'll see you next time, and we'll be back on Monday. Danny's Highway is going to be joining us as well, so. Okay. Sorry, Zach, go ahead.
No, I think I said what I was going to say.
Okay.
Subintervals, I think that's all I had to say. Yeah, subintervals basically
so negative
pi over 2 plus or minus pi down the number line.
Okay. So negative 2 pi to negative 3 pi over 2.
That's right. Yeah. I was being not specific, but yeah, we can go just like.
And actually, I should not. Yeah, that's fine. It'll be fine. And then negative 3 pi over 2 to negative pi. Yep. Union, and then we just keep going. That was maybe a mistake. With how many I actually have to write here. So. But also, when you think about it, as George Carlin says, this is also not the end-all be-all of the, yes, true. This is not the end-all be-all for these particular answers, because what we were talking about before is that for each of these, then we have to discern what the rectangle is going to be, the open rectangle, for that particular domain value.
You have to choose the right subinterval here.
Right.
And
which granted, right, if we're just talking x, we have solutions in every single one of these. That's fine. But then we say, okay, if we're going to do this right, let's take the middle one because this is going to be the easiest one. We have the rectangle. X is going to belong to negative pi over 2 to pi over 2, crossed with y belonging to what?
Are you talking about the y component? Like, so...
Yep.
The y component now. So you want the... What's our differential equation again?
Secant squared of x.
It's the secant squared of x. So you can do this for... let's see here. So you just do it in R, right? Because you can have an thing in R. As long as I'm... Let me think about that. You would do... Yeah, I think... Well, you have a bound of cosine for cosine squared. So, but your y values would be unbounded, yes? That's so R,
Sort of.
negative infinity to infinity, right?
There aren't technically any restrictions on y in terms of like having any actual discontinuities. There is,
however, what it maps to, right? You're gonna map to 0, 1. That much I didn't know. Again, I didn't know what you wanted to.
Yeah. So there's nuance here, and that's actually really important. So here, right, we see that all values negative infinity to infinity are possible. But for this particular function, we also know that y is not going to be anywhere from negative 1 to 1 exclusive. Right, so that space in between negative 1 and 1 is going to be empty. But that doesn't necessarily mean that like it's restricted. It's just that it just doesn't map there. Right, secant squared of x. Oop, go ahead.
No, you're fine. Actually, the output... So hold on a second. That's for the... I'm thinking of the solution. Never mind. But so here's the thing, though. You have to... Your solution will exist on... And so maybe we should clarify this for everybody. What specific rectangle are we talking about? Are we talking... So just for the benefit of the viewers, we should talk about where this rectangle exists. Is this in terms of our differential equation, or is it in terms of our solution? Right? So are we talking about the function from the perspective of the derivatives, or are we talking about the function from the perspective of just y, the solution y of x, in this case? Do you understand what I'm saying?
Yes.
Okay, so maybe I just need to, like...
No, that's all right.
I'll shut my...
No.
I'll shut my trap if you want me to. I'll be done. I'll be done.
No, I mean, we do need those discussions anyway. So yeah.
Right, so just emphasizing that when we talk about the solution, we're talking about an open rectangle with respect to the differential equation. I don't want to talk about the solution. It's where the solution will exist, right? But like, we're not talking about the solution itself. We're talking about where the solution will exist in terms of the differential equation.
Yes.
So I just wanted to clarify that as well.
Yep. Okay. So we're just making sure, right? We have this rectangle. We know that our initial condition, x0, y0, which will be the initial condition for the actual function. Did I get that right?
Actual function. So when you say actual function, what are you talking about?
The solution.
The solution. Right. So we're talking about the solution will exist on this interval.
Right. Yes. Okay.
That's what we're going for. So I'm imagining the XY plane in terms of this equation.
Right. So secant squared of x is going to have a solution that is on the x subinterval negative pi over 2 to pi over 2. And on the y interval, again, the function that we're talking about for the derivative is the secant squared of x. And that again, does not have any particular values between -1 and 1, but that doesn't mean anything in terms of the location for the solution. So we're saying that, like, yeah, sure, that doesn't map in this particular area, but there aren't any discontinuities in terms of, like, asymptotes or asymptotes. Let's go with that. That's all right. Okay. Hang on. Oh, Zach, I didn't share this. Jeez, sorry.
That's fine. No, you're fine. Just you keep going. I don't have a useful tablet to help you with, so yeah. I think it might be helpful if we just have it. I'm not opposed to share it.
I'll still just put it there, you know, in case.
That's fine. That's absolutely fine.
You could also circle stuff if.
Cool.
Okay, so this does not map to this particular area. Y is from -1 to 1, but these values are not restricted in the solution space. So one example where we might actually have a problem could be, for instance, if we had something like y prime equals xy, which is where I was going originally with this. Nope. Back up. X over y. There we go. In this particular case, right, this would not allow y to be equal to 0. And so here we would actually have like a restricted value. No, you cannot use this whatsoever in the original function, in the differential equations function, nor in the solution space. So y equals 0 is completely restricted. Can't use it. Okay. Okay. Anything else so far?
Keep going.
Right. All right, and then we'd also do the same for all the rest of these. Again, same rectangle is going to exist here for all of these individual functions. We're going to say, okay, it's the same y values from -infinity to infinity for all the rest of these x blocks as well, all the rest of the x intervals. We're also using the same y interval. Okay, so then, which one contains the point then? Again, pi over 4 comma 8. That's where we'd say, okay, that's going to be x goes here, and we're crossing that with y going from -infinity to infinity. Okay, how do we solve that particular differential equation?
Which one? Oh, by that one?
Y prime equals secant squared of x.
Yeah, y prime equals that. So you could just literally take the integral with respect to x, and I think that would do it.
Yep. So in this case, right, we've just got a derivative of something over there, and then we're going to say, okay, well, secant squared of x is going to be the derivative of something over there too. And we just happen to know what that derivative is. I will say in terms of style and my particular preference, I would actually split up y prime. And this goes back to what you were saying earlier, Zach. It looks nicer anyway. But in addition to that, we can move the differential. Because in this case, if you were to just draw in your integrals in this case, we'd have to come over here and be like, okay, well, what are we doing? There's something that's missing here, right?
Well, so I would just say you're taking the integral with respect to x, and then dy dx is a derivative with respect to y. So in some ways, I see nothing wrong with that, but
right,
it's fine.
So you do need to put in these things on both sides, and then it would work itself out in the end. My personal preference is to say, well, why not just take this and say, let's multiply dx to both sides. And so we end up with dy is equal to secant squared of x dx. This also means something in terms of our lesson for today.
And for those who are pedants, and if there's anyone who's like really
uninitiated,
uninitiated, like I don't want to call that sounds bad, but
well, I mean, those who have not taken this before certainly would have.
Like, there may be some who disagree with what just happened here. Theoretically, it's all fine. I was gonna say, Femvox, yeah, I'm with you. I love playing fast. It's totally fine. But for those who feel the need to be technical here, we probably just broke 1,000 rules for a pure mathematician. And I'm just saying, as a partial pure mathematician, I feel like I need to explicitly say that some will frown upon what just happened here today.
Algebraists won't care, though.
Algebraists won't care, and like physicists won't care. I can tell you that for sure. They generally will just do exactly what's been done, and it's fine. But if you have someone who, I find that the number of people who are angry about this are fewer than the people who are fine with it. So I just want to lose that as a footnote.
Okay.
It does work, Phobos. It turns out the answer is yes.
I mean, the entire notion of separability really depends on that. Is if you're able to split up a differential, differential term as dy dx into two separate pieces, one dy and one dx. So, like, if that didn't work, that kind of goes against the whole notion of separability. And we'll see more examples of it in second half of the program here.
Yeah.
Right, so in this particular case, we're going to say, okay, we're taking the integral of dy, which is then just going to be y. And then on the right, we're taking the integral of the secant squared of x dx, which is then going to be tangent of x plus c.
And to find a good reference on the theory, just rest assured that the analysts are now satisfied, but some may argue with you. My eyes, they're burning. Yeah, zone.
I mean, look, if they want to take it up, with you, that's fine. But they're going to have to deal with the other separability issues that come up later.
That's right. I feel obligated to say it at minimum, and at least acknowledge that some. Yeah. Anyway, I'll leave it alone. They're burned.
Okay. So I'm going to jump the gun a little bit and say, okay, what solution then is going to contain the point pi over 4, 8?
Oh, sorry, you're asking me.
Well,
So you could. I just didn't know.
Or chat.
I sort of
whatever.
don't know. That's fine. That's fine. I just don't know if I should answer chat or two. It's equals 7. Femfox says. Thank you.
right? Fair enough, because here, this is just an xy pair. So just go ahead and plug it on in, right? We get 8 is equal to the tangent of pi over 4. As we all know, that is just going to be 1. As we definitely all know, I'm sure. Everybody's favorite mathematician, math teacher phrases. Right, so we get c equals 7. Which means that so we use a word here to denote which solution we're finding. And we might have said it in Calc 2. But this one over here is going to be called a general solution. And this one here is going to be called a particular solution. Yeah, what particular word? You saw me stutter because I was just about to say it out loud.
Well done, Femvox. Well done.
Okay, so general solutions are going to just leave all of our constants undetermined in terms of what they might be, just because you could change which particular XY pair you have and get a completely, I mean, not completely, but get a different answer. So this one is y equals tangent of x plus 7. We could have y equals tangent of x plus pi over 6. Like, it probably would be disgusting, but, you know, could happen. I mean, x could just be 0. That'd be easy. At any rate, so we like to have our general solutions kind of highlighted and say, here's your general solution. And then also we like to have the particular solutions, if applicable, highlighted somewhere. Okay. So in addition to whether a solution exists, we would also like to know how might we be able to tell whether a given solution to a differential equation is a unique solution, so that there is no other possibility whatsoever. So I think this might actually lean more toward what you were saying earlier, Zach, unless I just don't understand what you were saying earlier.
Right, so, hold on, I have you partially on my audio. I don't want the crosstalk. So, I accidentally had that on. Anyway, what were we saying? So we have the uniqueness.
Mm-hmm.
You have you have the existence. So we've established that. And the uniqueness is where I think but you can still, you can do it with continuity as well. They're going to be very similar conditions here.
So
to what we had before.
1. Solution still has to exist. So go back to earlier, and we say, okay, we know that y prime equals f of xy is continuous. Cool.
But then you need some initial data.
Yes.
Too. So like you need some kind of y of whatever.
Right, whatever your initial value is that you're looking for, again, same deal as before. Is that thing going to have, is that function f of xy going to be continuous over that particular rectangle containing the initial point that you're looking at, x0, y0, and so now we need a second condition, which, I have it here, but Alright, so this one says that we need to take f that we had up above and take its partial derivative with respect to y. And then it must be also continuous on that rectangle, again, as defined above. Okay, so then if we have all this stuff, then there exists a unique solution. On, again, same sub-interval stuff that we were talking about before, A1, B1, such that x0 is going to belong to that sub-interval. I can shortcut that. No, maybe not. Wording-wise, it doesn't quite work. Anyway. All right, in this particular case, the one that we have up above is not particularly interesting. Just because if we say, okay, well, y prime was equal to the secant squared of x, and then we say, well, what's partial derivative with respect to y, right? We're taking the partial derivative with respect to y of secant squared of x, which is?
0.
Woo! Which is continuous everywhere, so...
Yay, right?
There's no particular issues that we're going to have there. And I want to say that I have an example here that's going to be different.
And Zone Ranger, you want to address the comment about R being the rectangle. That's what I'm understanding. I mean, I'm assuming
Yes.
that's the R you're talking about.
Yep. R is the rectangle. Boop. Thank you. Welp. All of the examples that I have here are exactly the same as same for existence and uniqueness. So that appears to be it's definitely not true for all functions, but at the same time, like, I just messed up in my examples. Harumph. Alright, well, anyway. So again, look at existence, look at uniqueness, and try to figure out over what sub-intervals of the original domain do we then have solutions at all, and then are those going to be unique solutions, the only possible solutions for that particular point. Okay. Any other questions out there? Boo. All right. That was DE4. Okay. Let's make sure that that's the right one. Okay. So, next question then. What would it mean to actually be separable within the context of differential equations? We've talked a little bit about this, but we're going to try to formalize it a little bit more.
Sure. So basically, and this is true for lots of differential equations, but if you can write your function as a product of two functions, like your dy dx, if you can rewrite that such that there's you have a function of x and a function of y separately, then we say the thing is separable. So you might say like an a of x and a b of y or something like that. M of x, sure, m works great.
Something like that.
Yeah.
All right, and what do you want to do with them?
Well, if we're allowed to split the differential, which I claim we are, we're just going to do it and be like Newton. Be like Newton, people, and be willing to split your differentials. So,
I mean, I think Leibniz wouldn't have a problem with it either.
I don't think I was going to say neither of them would have this. Dividing by zero is a thing, guys. It's all fine. Okay. So, so I just move. You have a dy. You move so divide by n of y and multiply by dx. Integrate.
Okay, so you're contending that the initial operation between them should be?
Product.
Okay. And there's multiple ways that you can do this. I know for ease of writing it, some other books go with dy dx should be a quotient.
Yeah, I've seen that as well. That's fair.
Just so that makes this n of y dy and m of x. Oop, gotta move.
One downside here in
dx.
doing that is saying that n of y is not. You have to have that condition in, otherwise. And ironically, you can only allow infinitesimal division by zero, right?
N of y is not going to be, certainly can't be, equivalent to zero. But also, like, if it is zero anywhere, it's going to potentially become a problem. But that's also going to be a problem in this product over here, where n of y is going to equal 1 over 0. But
you might want to pause for a second because we got an ad break.
Yep. So we're going to run the 3-minute ad break. I encourage everybody to get up, stretch, do your, cycle your water, and do whatever you need to. Grab a snack, and we'll be back in 3 minutes. Thank you very much, everybody. Oh, what? Did somebody already click?
You got kicked on. You got kicked on ad break with involuntarily. That's why I was stopping you.
Oh, already.
Yeah, so I got hit by ads just as you were talking. So
that's frustrating.
You may want to say what you just said again.
Because it says ad break in progress over on the left, and it did say ads coming up. So that's frustrating. All right, well, I guess we get 5 minutes or something like that. Okay, so we're going to go back just a minute here. We're going to try to do that again.
We're outside of ad break now, just so you know. So we're good to go.
All right, so apologies. That was not meant to go quite like that. I meant to do the full 3-minute ad break so that we could get an hour without interruption. Yeah, I know, that's... They were only 60 seconds. Arg. At any rate, in about 5 minutes or so, we'll go for a full 3 minutes so that we can get another hour out of it. At any rate, yes, so over here, Zach brought up a good point. N of y can't be equal to, can't be equivalent to 0, And we also say that it can't be equal to 0 at any particular point, because that's also going to cause a problem. And over on the left, we see that if it's a product, we're still going to end up with the same issue. It's just that internally, we have to say, like, n of y has to exist as a function. So it's probably a little less of a concern, because you can look at this and say, well, yeah, I mean, clearly if n of y is equal to 1 over 0, then it wasn't in the domain of it to begin with. So here we just have to be, like, domain conscious. But we always are anyway, because if you have a function, we're still going to be domain conscious about it. Over here, we just have to have a little bit more awareness that, like, hey, it can't be even 0. So, like, this is actually looking at the range of the function and saying, you know, the range of the function can't be 0. Do you want to add anything to that, Zach? Thank you, Rami. Welcome in. Righto. Okay. So then, if we go to okay, so we're going to, in general, solve the following separable differential equations, or show that they aren't separable. All right, where do we go from here? So in the first case, we've got dy dx is equal to x squared plus 1.
Oh, are you talking to me, or I don't know,
In general, you know.
Hey, is he talking to me? Right.
There's nobody else here.
I don't know. Like,
no.
So, okay,
sorry, going with the taxi driver bit.
Yeah, it's fine. Sorry, now I've got Rock'em Sock'em Robots stuck in my head from Toy Story 2. Hey, he was talking to me. Hey, he was talking to me.
Knock your block off.
Knock your block. Exactly. Integrate. So this one, I think we can just straight up integrate on the A. So y equals x cubed plus yeah. So you can. I'll let you write that down, but
again, integrate. My personal preference. That's just
sure. I get you. I get what you're saying. No, I mean, if you've never seen this before, it makes sense to write it down. And then we need to, if we're doing a general solution plus C, sounds great. That second one, see, we have the product of two functions already. So literally, I would just like separate the y factor and divide that. And then x squared dx, I think, is what you end up with. Those aren't too horrible. So then, what is it? Arctan of y.
I'll give you that one over there.
Equals, yeah, plus c. Yeah, and then the arctan of y on the left. That's an integral that's fun.
Yep, that's one that every Calc 2 student should have just nailed into their head by the end of it, because we used it so much.
Yeah.
So one of the interesting questions that we could probably ask a Calc 1 student would be, well, what about the plus C on the arctan side?
What about it? Yeah. So funny enough, when I taught, we got into an argument with C and where it goes and does it really matter. And in some cases, very much yes. It actually was one of the most productive conversations that whole semester. Was this argument about somebody was like, "Well, let's leave the plus C till the end," or "Oh, let's do the plus C in the middle."
Mm-hmm.
And like when we were solving something, and I was like, "Let's go down that path. Actually, that's a good idea." In this particular case, the plus C gets brought together, right? So you might say that the plus C on the arctan of Y, if you had a C1 and C2, that those could be combined safely because those are done sort of at the same stage. But as Finbox is saying, yeah, late Cs can be dangerous.
Yep.
100% agree.
So to any of those Calc 1 students who might not be aware, right, if you have a plus C that just pops into existence in both of these places at the exact same time, they're in the same place. So they're on the same level. They're both being added to both functions. And so what we do is we say, let's just bring those together. So subtract one from the other, and then here they show up as C2 minus C1. And so that's just another added arbitrary constant. So it doesn't matter what we call it. So at this point, we just say, let's combine them and just make it plus C. Makes things a lot easier. And yep, go ahead.
And you can treat them just as real numbers, right? Like the constants are just real numbers. If I take together, that's going to give you another. So in this particular case, combining them makes sense. Where you have to be careful is if you had, it's hard to create an example. I gotta remember what but it was, I think it was you had like x squared plus c under a square root, and somebody was saying that the plus c should be done later versus the plus c needs to be done under the square root, and it turned out that we got wildly different answers.
Yep.
When we did this. So be very, very careful to your c's.
Y to the, no, let's do 2/3, right?
Yeah.
So if it was
that might be
y to the 2/3, and again, we'd want the plus c here is equal to, 1/3 x cubed plus c, something like that. I think what you're saying is that the students didn't have this, and then took the 3/2 power here.
Well, no, that's fine. It was that they didn't put the plus c over on the end, like inside.
Sorry. What I meant was after. Then they do like this was
like,
y plus c.
Yeah.
Right. So let's do that, but this doesn't work because now we don't have this.
You didn't apply the plus c where it needed to be plus c, right? Like your plus c being a constant after a cube root versus before very much changes things.
Yeah.
And in the same way that this would be a horizontal shift versus a vertical shift. Like you might think of that as a... yeah. That very much changes the qualitative behavior of your solution.
Yep. Agreed. As somebody who, highly focuses on, in my pre-calc classes, doing functional transformations, right, every single one of these things that we do throughout the whole semester, I focus on, here's what would happen if we do... multiply by something on the outside versus the inside, and add something on the inside versus the outside, and make sure that we understand, like, these are 4 different things which, under certain function conditions, can have identical or similar behaviors. So, for instance, a horizontal compression of a parabola is going to be the same as a vertical stretch by its square. So
cool.
Okay. C.
Okay. Now this one, I want to contrast C and D a little bit because I like how C is written if you're separability versus D. They both seem to have this cross term, which is interesting, right? Like this xy and this xy squared, and you're multiplying functions of 2 different variables. The definition that we wrote down, though, at least the one that I gave, was where you had the product of 2 functions of different variables. And so can you write this thing in the C, part of this prompt C, as a product? And the answer is, in my mind, no. You can't write that, like separate that out of parts separately of two different variables, two different functions of two different variables. So definitely not.
Right, so in this case, yeah, this is not going to work. We could try to do stuff, so like, you know, factoring out the x would be the first go-to move probably for a lot of students. So like x times 3y minus 8x squared. Well, first of all, that is now going to leave 3y minus 8x squared. That's got two different variables inside of it in the first place. So that's kind of gross. And whoa. Ah, right. Because the... Yeah, okay. That's going to be a problem. Hang on. I'm smart enough I can figure this out, right? In theory. There we go. Yeah, partial selection does not select a thing, so that's good. All right. We could also attempt then to factor out the y from, right, these two terms, 3xy, and the plus y. So 3x plus 1 minus 8x cubed. Like, that seems to work upon first glance, where you might say, ooh, this is promising. But then we've got the other problem, and Zach already brought this up. That's not a product of two functions with mutually exclusive variables. So we can't make this into a single product. Now we've got this dangling minus 8x cubed on the end. And even if we tried to, like, for instance, divide by 3x plus 1, that's not going to actually get rid of it. It's just going to shift it. Oh, we wouldn't want to do that. Sorry. Divide by y. Right? Because if we had dy over here, dx over here, somebody might get the idea, I'm going to divide by y on both sides. But you'll notice I left something out. Right? We can't just divide individual pieces by y. We've got to make sure that all those pieces are divided by y. So even if this one went away and made this portion just a function of x, the last portion has now become a function of both x and y again. So we're stuck. And Zach, you said you wanted to contrast?
Yeah.
Because in the case of D,
so yeah, in D, x is a common factor, right?
love it. Yes.
And so now, if you factor x out, you can actually write this now as a product of two functions that are distinct variables, right? X is your one function, and y squared plus 1 over y is your other.
Right. So if we wanted to separate those by horribly drawn brackets, then here we've got our, yeah, x as one, and then the fraction as the other. And then we move that over by multiplying both sides by the reciprocal, so we get y over y squared plus 1 dy. And again, take integrals of both sides, and what do we get?
Let's see. So x squared over 2 plus c. That's your on the right. Which way you want me to do it first? Yeah, it doesn't. You want to do the left hand side, Obi? It's fine. It's fine.
Yeah.
One half
fine.
one half natural log of x y squared plus 1. If you want to do you can do the you would do a substitution here, an integration by substitution.
So u substitution, we're going to say like the whole bottom here is going to be our u, so y squared plus 1, and then our du is going to be the derivative of that, which is then going to be 2y dy. And we can't just make a 2 magically appear, so we have to multiply by a half to balance it out. So that's my preferred way of dealing with this stuff for Calc 2 students when we start getting into u sub. Calc 1, we talk about it like for a day. So anyway, we've got, yeah, the 1/2 here. We've got a du over u. So this is just the natural log of the absolute value of u. In this case, we don't really need the absolute value because the y squared plus 1 is itself always positive. But at the same time, it's nice to just remind ourselves that the absolute value needs to be there. Cool. So we just leave it there, right?
If you want to. I mean, depends on what we want. I mean, that is a valid solution. However, if you want a closed form thing, you can multiply everything by 2 and then take e to that. Because you could actually find c as is.
Mm-hmm. So if we multiply both sides by 2, right? Yeah, you could... That's also a good point. If we have an initial condition, almost. I would actually use it here. Right? Plug in all those values for x and for y, solve for c, because all you have to do is move the 1/2 x squared to the other side, and you have solved for c. So it makes it much easier to just do that. If we want to do closed form, again, multiply both sides by 2. This is going to leave us with the natural log absolute value x, y squared plus 1 is equal to x squared plus c asterisk. This is going to be a different c than it was before, but still, it is an arbitrary constant if you want to do that. So you're not able to just replace that c up there with this c down here, right? Don't replace this c with that c. Just interchangeably, they're off by a factor of 2. But nonetheless, if we want to move to closed form from here, we're going to do e raised to both of those sides. On the left, we just get y squared plus 1. And on the right, we get e raised to the x squared plus c asterisk. Right? Y squared is equal to. And at this point, you can also argue that there's a nice little way to manage. Silent Night, really? Not Christmas. Sorry, Zach, that was probably a non sequitur. Yeah, so over here we've got e to the x squared plus c, and we can separate that into two pieces, e to the x squared times e to the c star, which e to the c star is also just kind of an arbitrary constant. So we can say that this is also going to be e to the x squared times some other c value, some other constant. A lot of people don't really like it, but you know what, it works. Again, this is different, don't interchange it out of hand. And then the minus 1 that we move from the y squared side. Yeah. I really like it too, Femvox. It works so nice. Okay, and then again, if we're doing closed form, absolute value of y is going to be equal to the square root of all that stuff. So c e to the x squared minus 1. Okay, so yeah, this is going to be a closed form. It doesn't actually... Nice. Alright, this is not going to be a function of x, but it still exists as, like, a solution. And in fact, right, let's look at what this would look like. I'm sure this is fine. Absolute value of y is equal to square root c e to the x squared. Add a slider for c. Nice. Minus 1. Alright, so for c equals 1, we have this thing that almost looks like two tangent functions kind of diving at each other there. And if we increase the value of c, they separate into what looks like almost like hyperbola. Hyperbolae. Yeah, two branches because you have absolute value of y. Absolutely necessary. And if we go negative, it should just flip. Oh no, that's right. It goes horizontal. Oh no, that's not negative. Right. That is small values for c. And then if we go negative, it should make it small, like contained within a thing, I think. Oh no, right. Okay, it's negative. It's negative. I'm fine, I promise. Right, so we can't go past 0. Can't go past 0. So if c is small, we get these like vertical branches, which are horizontally symmetric about our y-axis. And then at 1, c equals 1, they're both horizontally and vertically symmetric. And then beyond 1, they're vertically symmetric. Nice. Alright, anything else to add?
Not at this time, nope.
Alrighty. Let's take that actual break then for 3 minutes.
Cool.
I don't think we'll go for the full hour, but kind of depends on how you're feeling.
Yeah, I mean, whatever, that's your call. It's your class, so you do your thing.
Okay. You know what? Let's just do the 1 minute, and that way we can get 20 minutes, which gets us to the theoretical end of class. So, we'll go to there. Alright. Everybody get up and stretch for 1 minute. Oof.
Is that it? So you got your
Yep.
20?
We're
Your
back.
20 in?
Yep. Unless it was 19 and I miscounted, but I'm sure somebody will yell at me.
Oh, there's my kid.
Yay.
Yeah, one of my kids came in and it's like, Dad! What fun times.
They're always the best.
That's right. That's right.
Okay. So, in lieu of me stretching, that's a good trade-off. I'll never get rid of all these channel points.
But do you have infinite?
Well, on Simplex I do.
On Simplex you do.
I'm
yeah.
using it on the Pez one.
Mm.
I have currently accumulated 285,000.
Oh my gosh.
Okay. So 3 we already talked about before. In what ways could we find a particular solution to these D's? And that was, again, just looking at trying to find either a product of functions to make it... Oh, sorry. Nope. Going back further. That was trying to find an individual value as our initial condition. Oftentimes we will call differential equations that include an initial condition an IVP, or initial value problem. So a lot of times you'll hear people just casually mention IVPs as some differential equations. That's what they mean. It just has an initial value that's given. So in this case, solve the following initial value problems. Let's make that bigger. All right, how should we do these?
Well, the first one is actually just the same as what we did before. We already know the solution to that one.
Right, so y as a function of x is equal to 1/3 x cubed plus x plus c. Right, and then?
So this is where we say things like, well, we know that the input to our function has to be 0, and our output has to be 7, so we could just substitute and solve for c. In this case, I think c will be 7, if I'm not mistaken.
Yeah, because this is a nice, easy one. It's a polynomial. So dump out all of our input variables as they are all 0, and they're all just additive terms. So 7 is equal to 0 plus c. So c7. And then we would want to say y is going to be equal to 1/3 x cubed plus x plus 7. As always, we want to start off with a nice, easy one. All right. I'm not going to regret this. What about the second one?
Well, so you want to break this one up, I think, into... we want to make it separable, right?
Mm-hmm.
I mean, that's one strategy here, is to make it separable. I don't know that you want to... Yeah, let's make it separable. Because you could do this another way, but I won't do that yet. So if you could just subtract y, I think, from sides of the equation, and then divide by the other factor.
Right, so if we kind of jump a little bit here, we're going to separate this into these two pieces. Right, move y to the other side, divide off the two polynomial parts, x plus 1 and x minus 2. And then we'll worry about the initial condition later, because right now we still don't know the general solution for this particular differential equation. Okay, now what?
So yeah, you can separate and integrate, right?
How so? Because I'm being a pain.
You're being a pain. Yeah, you are. So divide by y, multiplied by dx if you like.
All right, and I'm going to take the negative over as well, just because.
If you like.
There's a good reason. It's probably not a good reason, if that good of a reason, but. All right, then. Oops.
Well, integrate.
All right, left-hand side, we got negative.
What was it? Negative natural log y.
And absolute value in there as well, equals.
Now, I will choose to complete the square. If you'd like to, we can do a complete the square here, and that is completely legal.
Let's do it.
You want to do it?
Minus
okay,
X
I was gonna say if you want, because I know
-2?
I know what you were going for, but I'm gonna throw you a curveball.
That is
We do it
perfectly
by completing the square.
Absolutely.
I don't know. I don't. I think that might be the harder way, personally. I was being a little bit memeish, but if you really want to do it, but I just depends on what you want.
We do know that this needs to be of the form x squared plus, or minus in this case, I guess.
I will say partial fractions is there for a reason.
2a.
So like
x, yeah.
For the record, kids, if you're watching this and you haven't seen this, probably if I weren't being a little bit snarky, you might want to do the partial fractions method.
We will also do that one.
I was gonna say I recommend doing both here.
We could do partials on the next one, but either way.
Sure. Yeah. So x minus 1/2 squared.
Yep.
And then plus 3 halves. 3 halves? No. Sorry. Minus 7/4. No, minus 9/4. I can do this. I promise. There we go. 9/4 is what I meant.
Yep. All right, x minus 1/2 parentheses squared minus 9/4 is going to get us those two separate pieces. Right, so when we take the integral of dx over parentheses x minus 1/2 squared minus, and actually we'll say this is going to be 3/2 parentheses squared.
Mm-hmm.
Just cause.
That's what I recommend.
All right.
If you're going to go this route, I probably shouldn't do that, but okay, we've already gone down.
Too late.
I may as well. Can't turn back now. My own fault.
As always, of course, you can turn back and say, you know what, I don't really like this. Let's go a different route. But yeah. we being the math teacher types, we should probably show as many ways as possible.
Well, so if it were me, I would do a substitution here, and I would choose to make this so x minus 1/2 equals sine of u, or 3/2 sine of u.
Oh man.
You're the one who wanted to actually do it. I'm gonna blame you the whole way down. If you seriously took my advice,
This is an
I'm
Arctan,
being the
right? I
punk.
could just.
Well, it's not Arctan because it's not.
Oh no,
There's no
it's not
plus
plus.
sign.
Right.
No.
Yeah, it's minus.
So you're gonna have to do you're gonna have to do a trig substitution.
Okay, so
metric identities.
I think the way I would probably think of it is like, what if we actually just drew a picture for it? And yeah, we could automatically know which one to do, but for, again, students who are kind of newer to it, it might not be the obvious. So if we're doing something minus something, and those are squared, that's going to give us our hypotenuse. And one of the sides, I don't really care which one. Why did I do this way? Jeez. I'm at orienting the triangle, because... Right, that's silly. Let's do it that way, because now we're talking about that angle. It doesn't matter, I'm sure. But Alright, and one of our sides, so again, if we want to do sine, that would be our 3/2 out here. Okay, so then, is that c squared minus b squared is going to be a squared. Which is then going to be the cosine of theta times man, this music. Okay, anyway, cosine of theta is going to be equal to a over x minus 1/2. All of that is a. So that whole denominator is just going to be the cosine of theta. And then we have to figure out what dx is going to be. So that's where solving for x arg. Oh, no. Jeez. Man.
Inbox is right there, a squared. I think that might be something you're... I think that's, you'd want a squared, not a.
Yes, right.
That's, at least that's the... I'm pointing on the screen. I probably should be on the skeleton, but I'm pointing on my screen, like right here. You should see it, right? It's on my computer, not on yours.
Definitely.
No, there you go. But the a over 1, x minus 1/2, that's fine. The cosine theta part on the right.
Yep.
Okay.
But that's not constants and all that, so... Why am I having trouble with this? It's just
you
been
could always
so
try
long.
the substitution method.
Yeah, I know. Which way are we going with it? So that's... So we would want... You said x...
So I'd say x minus 1/2
Yeah.
is equal to 3/2 sine theta. And my reason for that is I'm trying to recreate an identity.
One more time.
So 3/2 sine theta, based on what you've written on the right.
Yeah. Right, okay, yeah. So that we can just replace that whole thing. 3/2 sine theta, all squared, minus 3/2 squared. and then that can factor out, and then our dx is going to be equal to 3/2 cosine theta d theta.
And this will actually work out nicely, I think.
Yep. It also gets
how
rid
it
of the
should
other
be.
stuff.
That is right, yeah. As far as I can tell, Femvox, that looks okay.
Yes, right, because this'll, yep, that changes. Okay, so 3/2 cosine theta d theta, taking the integral, and on the bottom, let's move this, because now we're going to need space. Right, we can factor out a 3/2 squared from the bottom, which then leaves sine squared theta minus 1. And we can also factor out a negative, which will switch those around, or we could just make it be negative cosine squared theta. So this is equal to, this is going to be a 3/2 on the bottom, which turns into 2/3 overall. Integral of, take out the negative, cosine over cosine squared is going to be d theta over cosine theta, which, yes, it is a secant. It's still pretty disgusting, but you know what? It's better than it was up there. So that was where I was going with it, but then I just decided to abandon it because it was giving me some trouble there.
Yeah, I might erase that or not use. I don't know. Yeah.
So the other thing will work. It's just a matter of, you know, not abandoning it. Oh, man. Okay, so both sides are now positive. I like that. Natural log absolute value y.
How's your integral of secant going?
2/3. Integral of secant is, what is that, absolute value, natural log of absolute value of secant plus tangent?
Secant theta, yeah, secant theta plus tangent theta. You really shouldn't have gone this route. I'm going to forever say, I wanted on the record that I said this as a meme. Actually took me up on it, so.
But hey, y is isolated, so.
You're not wrong. I will give you that.
So we'll go e and e like that. We got the plus here, which again is going to allow us to say that this is going to be a little c, which is e to the big C, multiplied by e to the, we can make this natural log absolute value secant theta plus tangent theta raised to the 2/3 power instead. Right, that's going to take that down. And then that leaves this with absolute value y on the left. And apart from rewriting it, that looks good enough for me. And I got rid of the absolute value on the right because we're squaring it, so either way it's going to end up non-negative, whichever way you write it. Right, and you know what, for completeness, let's definitely take a look at this and see what it looks like, because that's kind of cool. This is going to be absolute value y is equal to, we had c, e, nope, not e anymore, secant theta plus tangent theta, and raised to the 2/3 power. What do we have? Anything? Anything good? It's yelling at me. Uh-oh. We only support implicit
all,
equations of... Okay, whatever.
So here's the thing. Femvox, I was just going to suggest what Femvox said.
Yeah,
but,
I know.
you have to actually convert it back, unfortunately.
It's not that bad. So we had cosine. X was equal to... Nope, go the other way. Okay. So this was... Sine theta is equal to 2/3 times x minus half. Alright, it's going to be a little gross, but whatever, it's fine. If that's true, sine squared of theta is going to be 4/9. X minus half squared, which means that cosine squared, ew. It's going to be 1 minus 4/9 x minus half squared. Secant squared of x is going to be 1 over all that.
Now, conveniently, the tangent theta will have the same denominator, so we can use that to our advantage too.
Right, so that's just sine over cosine.
So you're basically, your solution is going to have the 1 plus 4/9 x minus 1/2 squared in the numerator for your inside the... If you like, you can do it that way.
Hate compound fractions.
That's fine. So then all you're doing is adding the numerators together, and you'll get the conjugate, in some sense, of the denominator.
Yeah, because the denominator, right.
Now, I will say, like I said, I'm going to repeat this over and over again. That other method probably would have been better.
Until we get to the end.
Stop listening to me, Obi, okay? Like, this is me.
Why, oh, why? Alright, so that's gonna go with...
I wish it was going to work out better, Femvox, but I don't think it will.
9 plus...
I want it to work better.
X minus 1/2. And then we just take all this, copy pasta, and switch. Hey. Well, that's fun. You get a Golden Gate Bridge sort of thing going on. Right, with some definite discontinuities. Yeah, I probably did just plug in secant squared, so you know what? That's fine. Oh, curses. Yes, I definitely did. Alright, so that's not quite the same, but whatever. It's going to be really close. Yeah, bat signal. Yep. Good one too. Yep. Alright, so this is going to be 3 plus, and again, good news, right? It's going to be all the same denominator still. Up top, just 3, and then plus twice the absolute value of x minus 1/2. Absolute value y. Alright, let's try that again. Oh. Okay, and then we take this whole bottom here. That's not gonna work very well. Alright, copy. Square root, put that in. Ugh. This might be super chunky, I can't tell. Yeah, it's very nice and pointy. As it gets close to 0, right, that starts like flattening out, but it's still a cusp. Simplifies enormously, but then again I cheated and used a part. That's not cheating though. It's just coming up with, or using a different method to get the same thing, so we're good. Okay, so if we don't use perfect square and instead use partial fractions, right, this gets us dx over x plus 1 x minus 2, okay, is going to be equal to, alright, then we go on an excursion, and we say down here 1 over x plus 1 x minus 2 is going to be equal to something over x plus 1 plus something over x minus 2. Multiply both sides by both x plus 1 and x minus 2. Terrible notation, but I'm going to do it anyway. Commentary is welcome. This leaves a times x minus 2 plus b times x plus 1, which means, so there's like multiple ways of doing this. You could decide which way is right for you. Some people say, okay, if x equals 2, then what we're left with is a 3b is equal to 1. And if x is equal to negative 1, we end up with a negative 3a is equal to 1. And so therefore a is equal to negative 1/3, b is equal to positive 1/3, and then we could just go back up top and say, our integral is now going to be dx over, this was a, so this is going to be a negative dx over 3x plus 1 plus integral of dx over x minus 2, and that's also times 3. Yeah, well. Easier, you know. Oh no. Definitely me. That's, yeah. Now you got me looking over in Discord to see who is on the call and desperately trying to get my attention. All right, so we have negative integral of that thing is going to be 1/3 natural log of absolute value x plus 1. Okay, and then plus 1/3 natural log absolute value x minus 2. Plus c. What do you mean this is easier? This is still equal to, what is that, absolute value of y? Right, I think. Oh no,
I think you're missing a minus sign.
Yeah,
You're missing a minus sign.
And also, e.
And also e, yes.
So this is not that. This is natural log, negative natural log, absolute value y. Okay. So from here we could do the same thing again. Make it 1/3 natural log, absolute value, x minus 2. Better not bring them together. Over absolute value x plus 1. I mean, I guess it doesn't really matter, right? We're having a day. It's fine. Do the e's. This is going to be e to the natural log of all this stuff raised to the 1/3 power, so get rid of the e in the natural log. It's just going to be the absolute value of x minus 2 divided by the absolute value of x plus 1, all of which is going to be raised to the 1/3 power. And that's going to be equal to, again, same thing, e to the natural log of absolute value of y raised to the negative first. Alright, so then switch which side everything is on by multiplication, and we get the absolute value of y is going to be equal to, this one flips, so it's going to be absolute value x plus 1 over absolute value x minus 2, all raised to the 1/3 power. Yes, the c went missing. That would be here, right? Yes. So that would be here. That would be here. Thank you. Why? Really? Okay. Do we not? Okay, yep, that's good. C times the quantity raised to the 1/3 of, this was x, which one was which? X plus 1 on top. No, goodness, they're not even remotely the same. This one looks remarkably the same, but over here we got a problem. I'm willing to bet that there's something else wrong up here. Actually, if we change this to 1/3, does that? No. Okay.
Is it the square root? Isn't there not supposed to be a square root on the
denominator?
The red graph? Yeah,
in the denominator?
C's might be different. Yeah, in the denominator. Is that supposed to be there?
Yes, the C's might be completely different. So
right.
The square root, or were they introduced at the same time?
Yeah, I'm venturing that they're going to be the same, but kids, this is why you generally want to take Occam's razor and choose the simpler solution.
Yeah, they do actually look like they're going to be the same, because they're like multiplied to C, or added. They would be multiplied to Y in the same way. Okay, so if I think the issue was if this was tangent squared and secant squared, right? We were saying we were just wanting secant and tangent to be added together. This is interesting, though. We'll maybe figure something out. Anders!
Hey, Anders!
Yep, that's fine. Don't worry about it. If you want to come in on any other ones, feel free. We'll be here all the month.
I'm gonna have to duck out for this class, I think.
Yep, that's fine. We're already 15 minutes over, so...
Yeah, I mean, this next one is going to be separable. You're going to use a similar strategy. If I am guessing here, you're going to be doing a partition thing again.
Yeah.
So.
And the other fun part about this one, this is our logistic equation that we were talking about last time, where we have a p-value and also a maximum p-value that are going to bound our p-primes. So, Andos, it's Monday, Wednesday at 8 o'clock UTC, or 2,000 hours, you know, whatever you want to go with. Yes, thank you. Yeah, Femvox. Right, so P is going to be increasing between 0 and 5. Yep.
Are you planning on doing something about the logistic equation in particular, or?
Eventually.
Or eventually, okay. I'm just
so we're going to
curious
get
what you're...
Later on, we're going to talk about the logistic equation in terms of, like, here's autonomous equations, but, like, it's not a... doesn't need to be, like, a huge deal.
Well, cool.
At any rate, thank you, Zach.
Yeah, thank you. I appreciate it, and I'm always glad to be here and help out.
Yeah, thank you very much. And wonderful discussions that go, you know, beyond what maybe I was planning on just saying out loud. But
I always hesitate saying things because I don't know what I should say or what I shouldn't say. Because on stream I'll say whatever I want, but like you know, not whatever I want. But Femvox is true. Don't overfish the pond is the lesson we learned from the logistic equation. I agree with that. Don't overfish the pond. Funny thing is, when I taught differential equations, that was a question on a midterm or a quiz once, was about fishing and making a model like that, and also about melting ice cream. That was another one. And what happens to ice cream when you put it out in the sun?
Nice.
Ambient temperatures are a thing.
Okay, right. Alrighty. Well, thank you, Zach.
It's always good to hear. I'm glad it wasn't just me, Femvox. I'm glad there are other people able to help. Yeah, you can do Mondays, Anders. That's awesome.
That's great. Yeah, Danny Highway's going to be doing the same.
Cool. Get excited, and we'll see you next time, I guess. I'll let you send off. I'll shut up.
All right, Zach. See you Monday. Everybody else, we're still going to stick around for a little bit here and do these last 2 bits. So on B, we completely forgot the point here. Right, we were doing the initial value problems just because we got kind of lost in the weeds there. It's fine. So y of 1 is going to be equal to -3. So coming to this one, obviously we like this one better. And again, because we got 2 separate solutions here, this is going to be slightly awkward, but like it'll be fine. We do like to consider that probably, right, it's going to be the one that oh, I see. You can't throw. Right, there we go. This is going to be our... Oh, right, it's a multiplier. C is a multiplier. So we're going to figure out what the multiplier C is going to be based on our initial condition, which was, again, y of 1 is going to be equal to -3. So we come in here and we say that we're going to get absolute value of -3. It's going to be equal to C times absolute value of x was 1 plus 1 over absolute value 1 minus 2 raised to the 1/3 power. Yeah, that's true. So we could at least check it and see if that's the issue. Add a slider for D. Probably not entirely the issue. Yeah, no, it's still not the issue. Because again, for some value, this should be the same, like identical. And it is identical for D equals 0.1, C equals 0.1, as long as we're between, what is this? Right about a half. And then forever. Actually, well, that's not even true because our above one just stops. Whereas this one continues out in both directions forever. Asterisk, I don't know if it's actually forever, but close enough. Okay, so we get here that 3 is going to be equal to C times the quantity. 2 over the absolute value of -1 is going to be 1. Raise it to the 1/3 power. So this is going to be C equals 3 times 1 over the cube root of 2. So 3 over the cube root of 2. And if anybody wants to yell at me about that, that's perfectly fine. So if we let C be equal to 3 divided by cube root of 2, and D is equal to 3 over cube root of 2. Nice. Again, we get that branch right here where it's going to nail it right on. So at x equals 1, y equals -3. Both of them go through that. And again, they should be identical, but there's this cusp here for our above one. There's probably something wrong in here. It probably has to do with this absolute value, honestly. Yes. Yes, it does. Oh, good times. Right, but we saw in both of them that they were the same. Or at least when we increase C and D at the same rate, that branch is identical minus the cusp. But again, that was because of the missing absolute value in there. It's fine. It's fine. Or extra absolute value. Let's just look at this real fast. I feel like that should still be there because this tangent should be like we're taking the square root of all this stuff, so it's here and there. And if x is, if x is less than a half, then we're going to get different values if we square it or if we don't. So, Ottos, we said earlier that we were having problems with this one, C. So Zach had stated that really what we want is for dy dx to be equal to the product of two separate equations, or two separate functions, each of which the product of two separate functions whose variables are mutually exclusive from each other. So we want one of them to be like m of x and the other to be n of y, and then to multiply them together. In the case of b here, right, it's just given as x squared times 1 plus y squared. That's easy enough. In the case of d, down here, we had x y squared plus x over y, but we could factor out the x and make it x times y squared plus 1 over y. So two separate functions in that case. Again, mutually exclusive variables. In the case of c, we were having a problem, because here, if we factor out the x's, then we have a mixed x and y inside the parentheses, and that we just don't want. And if we try to take the y from here and the y from here, we get this thing, which is going to be y times 3x plus 1 minus 8x cubed. And in this case, we can't separate the y from the x in either of these, right? If we try to separate it out like I wrote here, we divide it through and it ends up on the other one. So not able to actually separate them such that one side is x's and the other side is y's, which was the goal eventually. So we see here, right, what I chose to do was you take the differential dy dx and algebraically separate them. So you get a dy on the left and a dx on the right, then make each of the integrands only contain that particular variable. And in that case, we have a separable differential equation. So we got a little into the weeds with this problem here, but yeah, that's fine. Okay. P prime is equal to 2p times phi minus p. Right, and p of 0 is equal to 3. I think was my initial. Nope, p of 0 is 1. Okay. So we've gone way over time, but whatever, it's fine. All right, in this particular case, now we can do this again to make this a separable differential equation. We can say, all right, this is going to be dp dt, specifically in terms of like population, right? Population count over time, it would be dp dt. You can make up whatever independent variable you want if it's not given, which in this case it technically isn't. And again, this is going to give us all that stuff. So 2p times phi minus p. From here, in order to separate both sides, I would, again, multiply and divide accordingly to get all of the p stuff on the left and all the t stuff on the right. So in this case, dp is going to be divided by p times phi minus p. And that's set equal to 2 dt. You can choose however you want to like make this work. I'm just going to suggest doing it that particular way because it makes it a little bit nicer. Made you tune into finicky algebra rules? Yeah. Seriously. Yeah, so I mean, in a lot of cases it can't be done, but if you have, like, one of the general rules here is, like, if you have 3 separate terms that have 2 separate variables, and it's not, like, an easy factorization, then there's probably a good chance that you can't do it. Actually, a very good example of something that is definitely not separable is like y prime plus ty equals e to the t. Right? You're just not going to separate these variables. And this is an extremely common differential equation to see. We're going to actually talk about this one next class on Monday. So this is first order linear differential equations. It's an entire class of functions, or class of differential equations. We've already talked a little bit about it in terms of like, you know, what is this? What does it do? We've talked about the classification, but yeah, just that. No, you can't see that. This stuff right here is just really great. Yeah, first order linear differential equations, regardless of whether or not they're homogeneous. Are always just going to be solved, and are always going to be solved in the same way. Now, it may also be that we don't know how to solve some of them, because some of them have like really weird integrals, and you're like, well, I can't solve that integral. That's perfectly fine. Yes, those are the nice ones. And that's also one of the classes of differential equations that Leibniz solved. So I mean, like, this is the guy who originated differential equations, along with Newton. But like, the first guy who actually thought, hey, I probably need to teach this to kids, or, you know, students. Let's make sure that we actually talk about it and formalize it in a nice way. So over here, again, we run into the same problem with this denominator stuff. We're not going to be able to actually take the integral just as is, so we have to separate it. This is going to have to be done using partial fractions again. So 1 over p phi minus p is going to be equal to a over p plus b over phi minus p. If we want to leave it in the same form that it was before, right, makes it a little bit easier to work with. Multiply both sides by p times phi minus p, and we end up with 1 equals. A is then going to be multiplied by phi minus p, plus b is going to be multiplied by p at the end of it. And if p equals 0 or p equals 5, we're going to clean out one of the terms or the other, and so we just get, if p is 0, then we get 5a is 1, and if p is 5, then our a term is 0 and 5b is equal to 1. So wouldn't you know, they're the exact same thing. That's not what I meant, 5b. A. So a equals b equals 1/5. So integral dp divided by 5p plus integral dp over 5 parentheses 5 minus p in addition, that one is going to need a negative for, I'll just do that, it's fine, everybody probably understands. Right, we're going to need a negative for u substitution, so we'll just do that here with our dp and the sign that was out front. Alright, then that's going to be set equal to integral of 2 dt is just 2t plus c. Coming down, this is going to be 1/5 natural log absolute value of p minus 1/5 natural log absolute value of 5 minus p is equal to 2t plus c. and do e's again. This is going to stack up everything on the left and make it e to the natural log of the absolute value of p over 5 minus p raised to the 1/5 power. Clear the 5. Oh, multiply it to the other side. Yeah, that's also true. Because that also would have just been super easy to do. Is equal to e to the 2t multiplied by, again, lowercase c for a constant. Is going to be absolute value p over 5 minus p, so 1/5. C times e to the 2t. All right, and at this point, we could decide, do we want to do it now? Do we want to do it after? This is actually what Zach was talking about. If we do the initial condition here, we're still going to get the same answer, one way or the other, in terms of what C is going to be. But if we decide that we're going to clear the 5s, this would change that C value. And in this particular case, if we clear the 5 now, it's 1/5 as an exponent, we're going to have to raise both sides to the 5th power. So this C that we see right now is going to be the 5th root of whatever C we would get if we raised everything to the 5th power first. So again, kind of depends on what you want to do and when. Just keep in mind that the constants won't always necessarily be the same. You have to check all of your functions and make sure that they're working out kind of the same way. I know what I'm talking about, I swear. Alright, so if we do that stuff here, this was p of 0 is going to get us 1. So this was all 1s on the left. 1 over 5 minus 1 raised to the 1/5 power is equal to C times e to the 0, which is just going to be 1. So C is going to be equal to the 5th root of 1/5. No, 1/4. Jeez. Lol. Right. How you doing, Governor? Yeah, we're doing all right. Thanks, Megalomorph. How's the missus? She's doing very well. Woo! Ban. You guys got to work harder on that. Seriously. Does anybody think that actually works? Alright, so if we were to rewrite it as we have it, it's the absolute value of p over 5 minus p could also then be equal to the 5th root of 1/4 we're going to raise to the 5th power and just make it 1/4 times e to the, now e to the 2t is going to be raised to the 5th power as well, so that's going to make it 10t up there. And again, if we had done our p of 0 equals 1 here, we'd be able to see that again, this would be 1, this would be 1, this would all be e to the 0, so that'd be 1. So we just get a 1/4 is equal to, or c is equal to 1 over 4 on the left. So, yeah. All the same stuff. This does make it a little bit harder, but we're going to say here that as long as P stays within the bounds, when P is between 0 and, nope, not equal, 0 and 5, we have a positive value, and this still makes sense in terms of, like, we're not going to get a negative value for P if we're doing this for actual real functions, right? For an application function. If we're talking about the number of people in a population, right, we're definitely not going to have a negative value for that. Secondly, if you know that the population is above carrying capacity, that means that the population is going to start falling. And so we would know that since we're above carrying capacity, we would have a negative derivative. And so we would manually be able to say, all right, look, if P is greater than 5, we have a negative value. So we get negative 1/4 e to the 10t is equal to all that. All right, so when we do that, then we can say, all right, since we're going to stay within the P between 0 and 5, because our initial condition was P is 1, right? At t equals 0. So we know that we're going to be in this region, then we don't need to worry about the absolute value. You just say, yeah, we got it. P over 5 minus P is going to be equal to 1/4 e to the 10t. Yeah, right. Okay, so if we either multiply and shift stuff around, or we can potentially multiply both top and bottom by 1 over P, and then fix the fraction later. Right? We know it's going to be a compound fraction if we do that. It's all right. I hate compound fractions, but I'm willing to put up with it if it's going to get us a shorter process in the meantime. Right? So now what we can do is say, let's just flip the whole thing. So this is going to be 5 over P minus 1 is going to be equal to 4 e to the negative 10t. Okay, and we can add 1 to both sides. 5 over P is equal to, let's start with the 1 actually. 1 plus 4 e to the negative 10t. Right, and then we can multiply by P and divide by the whole E term. Knock it down in the other direction. So P is going to be equal to 5 divided by 1 plus 4 e to the negative 10t. This is our logistic equation. So this is what we were talking about earlier. Zach and I were discussing the, yep. Oh. Zach, you're gonna get the, you're not gonna be banned, don't worry. Right now. we're just going to have to go like this. And if anybody's wondering, yes, I am the artist of my own channel. I am actually looking to potentially get an actual artist, but it's going to take a while. At any rate, so we do have the logistic function here. 5 is a very important number. This is called our carrying capacity. This is going to be our maximum value that we can get in there. And both the 4 and the 10 have to do with the speed of increase. So what this is going to look like is, roughly speaking, something like that. Other names for this, we call it logistic. We can call the curve itself the sigmoid. I'm not sure if it has any other names, but those are the main two that I know. It probably has more, but at any rate, that is the solution that we get for this one. P of t is going to be equal to this whole function. And again, for this particular one, t equals 0, where p is 1. This is what we get here. We would have gotten a different c value sitting out front, which would, again, change the rate of increase. And you know what? No, it wouldn't actually change the rate of increase. It would be the exact same curve. It's just at what point is it, or at that particular t value, right? What is its p value? Gives us the starting population amount, which gives us the particular. It will tell us the rate of increase, or help it find the rate of increase. Because all it's doing is it's moving it to a different part of the curve. The curve itself is just moving left and right, yeah. Yes, it is an autonomous equation. We're going to talk more about that a bit later. They seem to be easy enough, right? We could probably talk about it, like, now, but I don't know why like everybody orders it in a completely different location. It's a little weird. But I guess they want you to have a few differential equations under your belt before they do autonomous equations. I don't know. I don't see much of a need to worry too much about it. So, this is what we've got for tonight. We had... Let's get the overview. So for anybody who wasn't here for the very beginning, we talked last class about classification of differential equations. They split into 4 categories that we really care about in terms of saying, like, these are the main classification types that get us different ways to solve the differential equations. We have the ordinary differential equations, they could also be partial differential equations if the derivative you're taking is multivariate. So if we have a single input variable and a single output variable, then we're going to, generally speaking, have an ordinary differential equation. It is of the third order because that is the highest derivative we are taking. It is nonlinear because the dependent variable has a nonlinear term. You are only looking at the dependent variable. It doesn't actually matter what the independent variable is doing. Here, natural log of x, here x squared, here 12x to the fifth. Doesn't matter one bit. This is only nonlinear because we have a y squared. If this was minus y, it would have been linear. That's the only problem with it, is just this y got squared. And it is inhomogeneous or non-homogeneous because we have a term over here, which is 12x to the fifth. It is of the independent variable only and is distinct from 0. So again, if this was equal to 2, or if it had like a, minus y squared plus 2 or something like that, it would still be inhomogeneous. Simplifying it to say it's just equal to 0, right? We don't always say that that works very nicely. We asked about, from last class, how might we be able to tell whether a given differential equation has a solution, i.e., does the solution exist? The solution will exist within a rectangle defined by the locations where our f of xy is equal to y prime will be a continuous function on that rectangle, whatever it is. We also said for functions like y prime equals secant squared of x, we were looking specifically on negative 2 pi to 2 pi, and we split that into its constituent parts. All of the discontinuities existed at our odd multiples of... Did I screw that up? I might have screwed that up. I did. Yay! Man. Okay, real quick. This stuff here. Right, negative pi does not give us a 0 for cosine function. So that should not be here. I thought that there were too many. I even commented that there were too many. So Zach, if you're watching this back, apologies. It's like perfect music for it. Great, thank you. Okay, and same thing here. This is fine, right. And then this one, again, the only reason that I had this one here was because the 2 pi is the end of our domain that we were looking at. Okay, let's go back then. So in the case of y prime is equal to secant squared of x, we broke negative 2 pi to 2 pi up by all of the locations where secant squared of x has a discontinuity, so that's all of our odd pi's on 2. And then all of these individual intervals can have some sort of solution on those intervals. We then said, well, it has to be a rectangle, so like in terms of y, where's that solution going to exist? And we said it can exist anywhere from negative infinity to positive infinity. In this case, right, our secant squared function is, technically speaking, going to be continuous on any particular y value. We don't have a problem with those. The only issue that exists is that the secant squared function doesn't have any values that are, you know, below +1. But it's not that it maps to it, is it restricted? So our problem was, like, if we had y prime equals x over y, y equals 0 would delineate two separate regions of solutions. So we wouldn't be able to talk about, like, guaranteed proof of existence along y equals 0. We just can't do it. All right. So existence proofs, we say, okay, it's just going to exist on any one of those domain pieces, crossed with our y values don't have any problems specifically. So we say anywhere from -infinity to +infinity. Now we have rectangles over which these things will have solutions. They are guaranteed to exist somewhere in there. That's also going to contain our starting point. Now, in the first place, we didn't talk about any particular point, so we just wanted to break it up into this stuff. But here I said, okay, which of these solutions contains the point? Pi over 4 comma 8. And then we could figure out what that was. Okay, c equals 7. We got this particular solution, y equals tangent of x plus 7. That also means that we're going to say that the rectangle in question is going to be from -pi over 2 to pi over 2, because it must exist somewhere within that, crossed with y goes from -infinity to +infinity. In order to determine whether a differential equation has a unique solution, we also take the partial derivative of f, in this case we're using secant squared of x, with respect to y. When we take the partial derivative of a function that is exclusively in x of y, then our derivative is just going to be 0, which is infinitely continuous. So no issues there. Most of the other ones that I had in my notes, everywhere that it existed, it also had a unique solution. So I've got to find a couple of examples that don't. And I will find some, I'm sure. Digital Selfie, thank you for the follow. We also have separability we talked about. So we said in order to be separable, we want that y prime to be able to be split into two separate functions which are mutually exclusive in terms of their variables and have a product or quotient of those things. So again, m of x times n of y will get us our separable differential equation. Once we do that, we then want to break this into n of y equals dy equals m of x. I said equals twice. N of y times dy is equal to m of x times dx if you did this as a quotient, or if you did it as a product, it ends up being dy over n of y equals m of x times dx. Either way, it doesn't really matter, right? Just separate your variables, get all the x's on one side, all the y's on the other. Doesn't matter which. And then we did some examples here where we made that happen, or in the case of C, we proved that that wasn't possible. So we're not able to separate this particular differential equation, but that's all right. There might be another method by which this works. We get to just figure it out later. And yes, that one will have another method. I need to take that down. So somebody remind me. We'll do that next class. Right, and then we said let's solve the initial value problems. So now once we get these particular once we get the general solutions like this one, we want to then plug in a particular point to get the particular solution. Yeah, it's very spooky music. Yes, thanks for coming, Zach. It's probably getting about dinner time. All right, and then we did the same with these other two, which we hadn't found the solutions, general solutions for yet. Again, one of them was very spooky, just like the music. Both of them ended up, we could use our partial fractions in order to separate, in order to get the separable equations to solve them into a nicer format. And at any rate, we end up with all this nice stuff. So for next class, again, what we're going to be looking at is what happens when we're not able to separate differential equations. Are there other methods for particular function types? Obviously, yes, I've just hinted that that's going to happen. We're going to be talking about specifically first-order linear differential equations, which again were generally solved for by Leibniz. He was able to come up with some pretty nice stuff. And then we're also going to look at, in order to solve first-order linear differential equations in a general sort of way, we're going to look at what are called exact equations. And we'll talk about exactly what that means when we get to it. For now, that is going to conclude class number 2 of differential equations. Thank you, everybody, for coming in and hanging out and having a good time. If you were at all interested in participating, if we know you already, i.e. you've been around in our streams and hanging out and stuff like that, feel free to join Penn Center's Discord and message me or, well, yeah, me for this class, Penn Center for complex variables. And Zach's going to have another class in end of summer. I don't think Zach's still here. Where's announcements? There's announcements. Thank you. Yep. Beginning of September through November, and it's called Infinite Series. Yep, thank you. And that is Zach at e to the 2i pi. Also has his own server. I don't have my own because there's just everybody else already has one, so it's fine. Okay. We're gonna see who else is on tonight. That's not at all what I wanted. Okay. Following. Stooky's online and has only been up for... No, they've been on for 3.5 hours. Okay. Well, we'll go raid Stooky. Okay. We're going to go over to Stooky's and raid over there. We're also going to... they're also on break just for the moment, but should be back within a few minutes, asterisk. I am also going to go check out Dawn's stream tonight, because Dawn is playing Outer Wilds. They say Dawn does math. And Outer Wilds is a really awesome game. However, if you have not played it yet, I would recommend going to do it. Absolutely going and playing Outer Wilds completely blind without knowing anything about what's going on. It's really awesome. If you're not really into exploration, maybe pass, but nonetheless. We're going to be back on Friday, asterisk? Yes, I think so. To do some game stuff. Probably going to be Zelda this week. We'll see how things are going, and whether my kids have confiscated the Switch to remain downstairs. So I hope you all have a good couple of days. I'll see you on Friday. I'll see everybody else on Monday if you're coming back for class. And then maybe some other times. We'll see how things are going and how I'm feeling. So, have a good one. My name's Obi-Wan Pez. This is N Simplex Pachinko. Have a good night.